So after the completion of these notes, you'll be able to solve a pair of linear equations by graphing, verify that the point satisfies an equation or system of equations, and solve a pair of linear systems by substitution. We'll also look at application problems involving linear equations and solving them. So let's look at what a linear system is and when they occur. So often in the field of electricity, some circuits can get pretty complex, and in order to express voltages or currents, you can get more than one equation with more than one unknown that need to be solved for at the same time. So they all need to be satisfied simultaneously. Okay, the ability to solve systems of linear equations is necessary in order to solve these practical problems. So a system of equations describes multiple equations that have multiple variables in them. And in this course, we're going to concentrate on systems of two linear equations with two variables. Okay, we've already done this in Excel, in fact. We've graphed two lines at the same time and identified the solution graphically by estimating the point of intersection. We're going to solve algebraically now using substitution. There's also another method which is commonly referred to as elimination and Cramer's rule. The other two methods, other than substitution, I'm just mentioning because they are commonly used and you will see them in different textbooks and online resources. But the reason we focus on substitution is because it's a method that can be applied to nonlinear systems as well. So you can use it for linear and nonlinear. And we're going to solve this system of equation graphically. So we have the system of equation 2x plus 6y is equal to 12, and 2x minus y is equal to 12. If we were performing this in Excel, we would solve for y by getting, we divide everything by 6, and you would get y is equal to minus 1 over 3x plus 2. And for the second one, you would get y is equal to 2x plus 2. Okay, so that's just a reminder when you're graphing in Excel, you need to isolate for one of the variables first, and then you list your domain, your x values in the first column, and then the next two columns would contain each of these equations using cell referencing, and then you would plot the graph below. Okay, once you've plotted them, you could determine the point of intersection by estimating here. It looks like it is exactly 0, 2, right on the y-intercept actually of each of those lines. That doesn't always happen. But if we solve for this system of equations algebraically, we should get the exact same solution. We should solve for the point of intersection being 0, 2 as well. So before we look at using substitution, we're going to talk about the nature of solutions, so the types of solutions that you can end up getting when you're dealing with a system of equations of two lines. The first case is where you have two lines and they intersect at exactly one place. So this is where you have one solution, one point of intersection. And the second case is where you have two lines and they're actually two equal parallel lines. So if our first line is identified right here, our second line, it might be a scalar multiple, so it might look like it's a different line, but every single number in the equation is multiplied by the same number, and it in fact describes the exact same line. So my second line would go right over top of my first one, and our point, they would intersect every spot along the line. There's an infinite number of points of intersections, so they actually intersect everywhere. So an infinite number of solutions in this case. And the third case, So we've talked about parallel lines and what's required to have a parallel line, but so you can have parallel and equal lines, or you can have parallel lines that have a different y-intercept and never intersect. I'm just going to put a symbol in here for being parallel. So we'll call these parallel and not equal lines. And there is no solution in this case. They never intersect with each other because they're parallel. They go on and on and on forever, but they never cross. Okay, so that's just so that you're aware of the type of solutions that you can get when you're solving. In this course, we're going to be mainly looking at the first case where you arrive at one solution. In your textbook, there are examples of all three of these. Okay, so with substitution, you look at both your equations and rearrange one equation to the form y is equal to or x is equal to. So we're isolating for one of the variables. Okay, I should mention that in this process, there's many different choices that you can make. You can make different choices than someone else as long as you perform all the steps mathematically correctly, then you will arrive at the exact same solution. But there are some steps that can be easier than others if you see some tricks along the way, but you actually can't go wrong making any choice as long as you perform the algebra correctly. Okay, so next you substitute the rearranged equation for the variable that was solved for into the other equation. Step 3, we solve the substituted equation for the single variable that's remaining. And then step 4, substitute the value that we've solved for back into the other equation. And then we can check our final answer by substituting both the variables back into one of the equations and seeing if the equation is still true. So this is a check where you're checking that left side equals right side. I actually like to say it's good to check that they work in both equations because sometimes you can make a small mathematical mistake and when you sub it into one, it will be satisfied, but not into the other. And then you would know that you made an error somewhere, so you should check. So I'm going to leave those steps there as something you can refer back to after you've had some practice, but the best way to learn how to do this is to see it demonstrated using an actual example. So we have a system of equations. It's a linear system because both of the equations describe lines. We have 2x plus 3y is equal to 13 and 2x minus y is equal to 1. I've labeled these equation 1 and equation 2. So we take a look at these equations and determine, is there a variable that's easiest to solve for in either of the equations? And I would say that from equation 2, we can easily solve for y, and we find that y is equal to 2x minus 1. So what I did is I brought the y to the right-hand side, and I brought the 1 to the left, and we have an equation for y. We want to sub that in to the other equation, so equation 1, and then we get 2x plus 3. Everywhere there's a y, we're going to put 2x minus 1, and that's equal to 13. Now we have an equation that only contains one variable. So we can use that to solve for x. So distribute the 3 into the brackets, you get 2x plus 6x minus 3 is equal to 13. Reduces to 8x is equal to 16. Can put an extra step in here where we have 13 plus 3. So 8x is equal to 16. Therefore, x is equal to 2. Now we know what x is equal to. So sub x equals 2 into y is equal to 2x minus 1. So when we sub that in, you get 2 times 2 minus 1, which is 4 minus 1 is 3. Therefore, solution is 2, 3. For step 5, the check, and I'm not going to show this every time, but I'm going to show you for this one. We check equation 1 and we check equation 2. The left side of equation 1 is 2 times x, which is 2, plus 3 times 3, which is 4 plus 9 is 13, and that's your right side. So you can see this check I'm doing is not very formal, but you're looking at the left side separate from the right side and showing that they equal one another. Okay, equation 2, you get 2 times 2 minus 3, which is 1, which equals your right side, so it's correct. Often to do this check, I actually just look back at the 2 original equations, I sub the values of x and y into them, and as long as left side equals right side on my calculator, I'm comfortable to move on and know that I didn't perform or make any mistakes. Okay, so that's how you can solve for this algebraically. If you were to graph these lines in Excel, you would find that they intersect exactly on the point 2, 3, which is the same as what we calculated algebraically. So your answer will be the same. We have a couple practice problems now. They vary in difficulty, mostly because of the numbers, whether or not you're dealing with decimals or whole numbers. But I want to encourage you to pause the video now, try them on your own, and refer back to the solutions. Okay. So for question 1, we have 2 equations. From equation 2, I'm going to solve for u. So we get 5v plus, okay, sorry, I'm going to bring the 5v to the other side. We have 2u is equal to 16 minus 5v. Now, to solve for u, we divide both sides of the equation by 2. You get 16 over 2 minus 5v over 2, which is 8 minus 2.5v. Now, sub u into the other equation. Sorry, we were working with equation 2, so now we need to sub it into equation 1. And you end up getting 3 times 8 minus 2.5. V is equal to 5 plus 2v. So wherever there's a u, I plugged in my equation for u. Now you distribute 3 into the brackets. 3 times 8 is 24. 24 minus 7.5v is equal to 5 plus 2v. You bring everything with a v to one side of the equation. You get 2v plus 7.5v on the right and 24 minus 5 on the left. This reduces to 9.5v is equal to 19. Therefore, v is equal to 19 divided by 9.5, which is equal to 2. Now we sub v is equal to 2 into u is equal to 8 minus 2.5 v. And what that works out to is u being equal to 3. Therefore, our solution is uv is equal to 3, 2. Okay, again, if you're wondering on a test or other assessment if your answer is correct, you take your solution, sub it into each of the equations that you started with, and you should find that the left side equals the right side if the solution is correct. Looking at question 2, we have a lot of decimals to work with. There's different ways you can approach solving these. You could multiply both equations, so equation 1 and equation 2, by 4 to clear the decimals. You'd be working with slightly bigger numbers. Or I can show you another way. So from equation 1, let's solve for I2. So 0.25 I2 is equal to 5 minus 0.75 I1. To solve for I2, we divide both sides of the equation by 0.25. And we find that I2 is equal to 20 minus 3 I1. Now sub I2 into the other equation, so into equation 2. Therefore, we get 0.25 I1 plus 0.75, 20 minus 3i1 is equal to 4. So even though there's decimals and it looks, you know, quote unquote ugly, not very nice to work with, you'll still get the same answer, and it's still the same as just working with integers. So we distribute the 0.75 into the brackets, and you get 15 minus 2.25 I1 is equal to 4. We solve for I1 now. So you bring everything with an I1 to one side of the equation. Let me just show this in more detail. So when we simplify the left side, we get negative 2I1. And on the right-hand side, we get 4 minus 15. Yet negative 11 is equal to negative 2I1. Therefore, I1 is equal to negative 11 over negative 2, which is positive 5.5. And it has units of amps. At the very start of the question, we were told that I1 and I2 represent currents in amps. So our final answer should have units of amps. And also, we need to solve for the other current now. Therefore, I2, we said I2 is equal to 20 minus 3I1. So 20 minus 3 times 5.5. And you end up getting 3.5 amps. Therefore, solution is I1 is equal to 5.5 amps and I2 is equal to 3.5 amps. Okay, then looking at question 3, we have the sum of two voltages is 120 volts and the difference between them is 24 volts. We want to find each voltage. Okay, we could actually just leave the question there, and I didn't have to give you what x and y are equal to or the equations because we actually have enough to build the equations. The fact that the sum of the voltages is 120, we know that if we add two voltages together, it's going to equal 120. And then for the difference of them being 24 volts, in order to define difference and having a positive difference, we need to know which one is larger. And so that's why we define one of the voltages as being the large one and the other one being the small one. Okay, so looking at equation 1 and equation 2, we can solve for it. So from the first one, it's really easy to solve for x or y. It doesn't matter which one you solve for. We can solve for x is equal to 120 minus y sub x into equation 2. Now, when we solve for y now, well, let's sub it in first. So you get 120 minus y is equal to 24. And we get 120 minus 2y is equal to 24. 24 minus 120 is equal to negative 2y when you bring the 120 to the other side. Now divide both sides of the equation by negative 2. I guess I probably should have shown one more step there. Let me just write that out again. So we had minus 2y is equal to 24 minus 120, which reduces to negative 96 is equal to negative 2y. So y now, divide both sides by negative 2y is equal to 48 volts. And sub y is equal to 48 into x is equal to 120 minus y. And we find that x is equal to 72 volts. Solution is xy is equal to 72 volts and 48 volts.